In this section of Chapter 8, I would like to go over transition metal ions and then heat of reaction calculation from bond energy. Transition metal ions. Just to remind you, if you look at periodic table, the elements in the middle section of periodic table that begins with 3b are transition elements. So it goes on like from 3b, 4b, 5b, 6b, all the way to 2b on the other end. And these are all within the middle section of periodic table. And these are transition elements. They usually give colored compounds, and that their electron configurations, especially the ionic forms, are a little bit different from the electron configuration of non-transition elements, especially when you're trying to remove electrons from these elements. For example, titanium has argon configuration followed by 4s2 and 3d2. Make sure you look at periodic table when I'm going over this. When you want to get titanium plus 2, that means you need to remove 2 electrons. Those 2 electrons would not go from 3d, rather it would go from 4s. So that's the major difference between transition metal ions and non-transition metal ions. They usually go from the closest s subshell rather than the d subshell. Non-transition ion, for example, here I have written down carbon 1s2 2s2 2p2. When I get carbon plus means plus 1, you remove 1 electron, and that electron would go from the outermost 2p subshell, for which we get 2p1. So this is distinctly different from transition metal ion configuration. Now we discuss the strength of covalent bonds and calculation of heat of reaction on the basis of bond strengths. Now, we'll go over a number of bond strengths, but here, just for the sake of explanation, I'm giving you a number of bond lengths as well as their bond strength. Carbon-carbon single bond has 348 kilojoule per mole. What that means is, if I want to break a carbon-carbon single bond, I need to apply 348 kilojoule of energy for every mole of carbon-carbon single bond. When there is a double bond, in order to break that carbon-carbon double bond, I need to apply 614 kilojoule for every mole of double bonded carbon. Similarly, for triple bonded carbon, the energy would be 839 kilojoule per mole. Now, these are bond breaking energy. What would happen if I'm making those bonds? For example, if I bring 2 carbon atoms and make a single bond, it would be just the opposite sign. Here, bond breaking needs energy, bond making gives off energy. So for bond making, let me write down here, bond making, it will be just the opposite of bond breaking. Book gives all the bond breaking energy, and that's how they're tabulated. And so it's the bond making. If it's a carbon-carbon single bond, bond making energy is going to be minus 348 kilojoule per mole. So make sure you understand this. Now, how do I understand that in order to break a bond, I need to apply energy? Keep in mind, bond means force of attraction that holds atoms together. Just like when I have 2 magnets, North Pole and South Pole, if they're facing each other, there'll be an attractive force. In order to break that bond between these 2 magnets, you have to apply energy so that you remove this one magnet from the vicinity of the other. Similarly, in order to break a bond, break their attractive force, you have to apply energy. Now, the table here shows average bond enthalpies of bond breaking energies. Now, why we use the term average? Because different bonds, as you see here, for example, carbon-hydrogen bond, the energy is shown as 413 kilojoule per mole. But keep in mind, you can have carbon-hydrogen bond in methane, you can have this carbon-hydrogen bond in ethane, in chloroform, and many other carbon compounds. So in every carbon compound, carbon-hydrogen bond would not have same strength. So there would be some variation. And that's why all those are taken into account. And that's why this is an average of all those values. Same is the case with other bond energies. So even though in book these are listed as average bond enthalpies, but keep in mind these are nothing but bond breaking energies. They don't write down bond making energies, because bond making energy would be same in magnitude, but the sign would be opposite, because energy would be given off when you make a bond. In this table, we are looking at different types of bonds, like carbon-carbon single bond and their length. 1.54 is single bond. Double bonded carbon has 1.34 angstrom. Triple bond has 1.20. So as number of bond is increased between two atoms, the length gets shorter. And that's understandable, because bond means force of attraction. Double bond means more attractive force. Triple bond would be even more than that. And that's why I need to put extra energy. Now here, even though I don't have the energies right here, but in previous slides, I have shown you their energies, and you'd see consistently from single bond to double bond to triple bond, bond energies are increased. Same is the case with other types of bonds, carbon-nitrogen bond or carbon-oxygen type of bonds. So keep this in mind as the bond order. We call this bond order. That means from single bond to double bond to triple bond is increased, bond length is decreased, but bond energies are increased. That means you need to apply higher amount of energy to break a double bond or triple bond compared to a single bond. Let me go over 8.69b, which is page 326. So let me first write down the question. CH2, then double bond CH2 plus HC triple bond N, that gives CH3, that's the methyl group, and then CH2, and then you have C triple bond N. Let me double check whether I copied everything right. So make sure you should also double check. Okay, now the question is asking for what is the delta H, or heat of reaction, for this reaction. So you estimate these based on bond energies, and those where you get all these bond energies from the table that I referred to. And if you have 12th edition book, you'd find these values in table 8.4 that has average bond enthalpies. So let me copy these values from the book. Before that, let me find out and question which bond I need to break on the reactant side. Focus on the reactant side. Question is, do I need to break C double bond C? How do I understand that? Look at the product side. Is there any C double bond C on the product side? No. So you need to break C double bond C on the left hand side. And in order to break that bond, you need to apply energy. So C double bond C has the energy of 614 kilojoule per mole. So let me write down that. 614 kilojoule per mole. What about carbon-hydrogen bond on the left-hand side? Do I have to break those? No, because look at all this carbon-hydrogen bond on the right-hand side. We have altogether 1, 2, 3, 4, 5. 5 carbon-hydrogen bond on the right-hand side. And we also have 1, 2, 3, 4, 5 carbon-hydrogen bond on the left-hand side. So there is no need to break carbon-hydrogen bond on the left-hand side. It's pretty much like kids when they make a toy by breaking the original say statue or whatever they have, and they're trying to make something different. So they break the given one and try to make a different one. So in this case, we are starting with what we have on the left hand side, and we're trying to make what is on the right hand side. Okay, now let's question C triple bond N. Do I need to break this bond C triple bond N? Well, on the right hand side, on product side, I have C triple bond N. So I don't need to break C triple bond N. So only bond breaking energy that I need would be to break C double bond C. Now let's now focus on the right hand side. Is there any bond that I need to make which didn't exist before? Again, comparing the reactant side, we find that there was no CC single bond before. So you need to make this. So then you look at the table 8.4. Let me refer to that table 8.4. So let's write down here table 8.4, which lists average bond enthalpies for 12th edition textbook. Okay, now I have CC bond energy, so that's I need to make that bond CC single bond, and CC single bond involves 348 kilojoule per mole. Now keep in mind there are two such CC bonds. This is one of them, this is the second one. And this would be energy given off because they're making it. So this would be minus 348 times 2. It's a very common mistake that students often forget to take into account the right number of bonds. But in this case, there are two such CC bonds. Because on the left-hand side, there was no such CC bond. So both the CC bonds has to be made new on the product side. Okay, when you do the math, you're going to get minus 82 kilojoule. So this is minus, don't forget to assign negative, minus 82 kilojoule. That's exothermic reaction. So that's the delta H value for this reaction. Let me now go over 8.70C. Okay, the question that I'm going to first write down is NH2 and H2, and then there is another NH2 group plus Cl2, that gives two moles of, or 2 molecules of H and H bond and then Cl bond. Let me double check whether I copied everything right. NH2, NH2, and then ClCl gives 2 NH2Cl. Okay, now again it's the same kind of question. Is the calculate heat of reaction or estimate heat of reaction based on bond enthalpies. Okay, now here we are also going to ask the same question. Which bond, which is the minimum number of bond that I need to break, and on the right hand side, which is the minimum number of bond that I need to make? Well, if you don't want to think about bond breaking and bond making, then break all the bonds on the left hand side and make all the bonds on the right hand side. This is going to take longer time if you break every bond and make every bond on the right hand side. But if you can find out minimum number of bonds that you need to break, then that would save a lot of your time. But be careful not to miss any bond that you need to break or make. For example, NH bonds. I have 1, 2, 3, 4 NH bonds on the left hand side. Even though it looks like I have 2 NH bond on the right hand side, but truly it's multiplied by 2. So it's multiplied by 2. Actually, there are also 4 NH bonds. So I don't need to break any NH bond. However, NN bond, do I need to break an N bond? Yes, because on the product side there is no NN bond. So you need to break it here. Now again, look at the table of bond energies, and you find that the energy is 163 kilojoule per mole. 163 kilojoule per mole. That you need to apply. That's why it's positive. And book always lists the bond breaking energies. What about Cl-Cl bond? On the right hand side, product side, there is no Cl-Cl. So you need to break this bond. In order to break Cl-Cl bond, we need 242 kilojoule per mole of such bond. Okay. Now on the right hand side, NH2, we don't need to make it because it was already there on the left hand side and we kept them. However, we need to make a new bond here, NCl bond, which we didn't have on the reactant side. Now if you're making it, how many of these you're making, even though it's like only one bond, but keep in mind it's multiplied by 2. You can also think it by writing NH2Cl twice. So this would be basically minus 2 times 200 kilojoule per mole. Why times 2? Because there are 2 such molecules, and each molecule has one NCl bond. So 2 molecules would have 2 such NCl bond, and each such NCl bond requires minus 200. So that's why 2 times minus 200 be minus 400. Now if you do the math, you're going to get 5 kilojoule. And this time is positive. So heat of reaction for this reaction is 5 kilojoule.